Welcome to Communication Lab. In this lab, we plot frequency response of pre-emphasis and de-emphasis circuit. Our aim is to design and plot frequency response of pre-emphasis and de-emphasis circuit using op-amp. Before we design, let us understand what is pre-emphasis and de-emphasis. So pre-emphasis is a technique which strengthens the higher frequency signal before the transmission. So that is generally called as high pass filtering. The de-emphasis circuit is opposite of pre-emphasis, where artificially boosted high frequency signals are brought back to their original amplitude. So this circuit works as low pass frequency. So we are now going to design two filters, high pass filters and low pass filter. So what are the application of this pre-emphasis and de-emphasis circuit? Pre-emphasis circuit finds very important application in FM broadcasting so that it improves signal to noise ratio. In speech processing also, this pre-emphasis circuit is used for compensating the speech signals. RS-485 communication, which is used for distance communication, reliable on this pre-emphasis and de-emphasis circuit. So skin effect compensation, where a high frequency current flow on the surface of conductor uses this type of circuit. So once the filters are used, so what are the components required? We need RC component, that is resistance, and capacitor components along with the op amp here. Along with these discrete components, we need dual power supply, function generator and CRO. Schematic representation of dual power supply, function generator and CRO is mentioned here. Whichever the essential terminals that we are using or switches we are using or the controls we are using in dual power supply, function generator and CRO is mentioned here. So this is the pin configuration of op amp with inverting terminal, non-inverting terminal, output terminal, positive and negative power supply. So once the components are known, so it is to design the values of the component. So for pre-emphasis and de-emphasis, for RC component, the standard value of T, that is taken as 75 microsecond. Assume capacitor value as 0.1 microfarad, substitute to find the value of R. So on substituting the value of T and C, approximately we are going to get the value of resistance as 820 because 750 is not available. Next standard value is 820. Since the op amp we are configuring in non-inverting configuration, gain of that op amp is given by this expression 1 plus feedback resistance by R1. So for op amp non-inverting configuration, let us consider voltage gain 1.586. Substitute and solve for RF and R1. Since both are unknown, RF is 0.586 time of R1. So assume R1 is equal to 1 kilo ohm, then RF we get 586 ohm. If this is not available, let us go for the other values of RF, that is 560 ohm is available. Once all the components are designed, so let us connect the circuit. As mentioned, some of the control signals of some of the controls of function generator, power supply and CRO is shown here. Not all the controls are shown here. This is the schematic representation of the instruments that we are using. So connect the op amp to the breadboard, connect the resistors and RC element, and you can connect the input and output and the power supply as shown. So the next very important thing here is, what are the steps to get the required frequency response? Always the step one is to set the signal. So on function generator, select the sine wave, keep any frequency. So you set 10 volts peak to peak by turning this level knob. After that, press 20 decibel switch, connect the CRO cable to the function generator. Observe whether you are able to see clear 1 volt peak to peak signal or not. Here you have to observe, you have kept the volts per division 1 volt. So what is the meaning of volts per division is equal to 1 volt? So you are clearly observing positive peak and negative peak within one block. That means peak to peak amplitude is 1 volt. So in the next step, you have to verify the power supply connection that you have given to op amp. Plus 15 volts to 7th pin, minus 15 volts to 4th pin, and common ground you have to connect. So if these pins are reverse connected, the IC may get damaged. Or if ground is not connected, by just connecting these two terminals, then you won't get any output. So once the connection is verified, turn on the function generator, turn on the power supply and CRO. Now you vary the frequency from 100 Hz to 10 kHz in steps using the coarse knob in function generator. Note down the corresponding output on CRO by keeping the CRO in XY mode. Then tabulate the results for plotting the graph. After tabulating the results, this is the values that we have obtained. So for 100 Hz to 10 kHz, we have obtained output voltage here 0.2 volts to 1.4. Use the gain formula 20 log V output by V1, because V1 is 1 volt. So you are going to get here 20 log V out. Calculate and tabulate the result as shown. So this is the semi-log sheet. You have to plot the graph. So on semi-log sheet, the frequency I am going to start here is 100, and the last frequency here in this first column of frequency is 1000, that is 10 divisions. So here you can observe the values of the frequency versus gain. On y axis I have considered gain, and on x axis I have taken frequency. That is nothing but log scale on x axis and linear scale on y axis. So now you identify the points where you want to plot. So here we are able to see on x axis. On x axis I am able to see here the values. For 100 Hz it is minus 13. So here we are plotting or marking. Then for 200 Hz it is 0.3, it is minus 10, so we can plot here. Similarly for 300 it is minus 7.95, so this is 10, so this is 8 approximately we can consider here. So like that you mark all the points on the semi-log sheet like this. Now you join the graph in order to get the smooth curve like this. Once the smooth curve you got, it is the next very important point to obtain the cutoff frequency. So how to obtain the cutoff frequency? So we have to now identify the 3 decibel. So this is the maximum value we got. From the maximum value, calculate minus 3 dB. So this is 1, 2 and 3. So draw one horizontal line. So it intersect the graph at this point and draw vertical line. So note down the frequency. We got here 1.6 kilohertz for pre-emphasis. In a similar way, interchange the value of R and C. Instead of C, put here R, and instead of R, put here capacitor, and follow the same procedure. The results are obtained like this from 100 to 10 kilohertz. So this is the graph that we have obtained. So for 100 hertz it is 4, for 200 it is 4, up to 500 it is 4. After 500 we got for 1000 1 kilohertz 3.52 and it is reducing. So now identify minus 3 decibel from the maximum here 1, 2 and approximately 3 here. So draw one horizontal line, it will intersect the graph at this point. So draw vertical line, you will get 1.9 kilohertz. So that is how we are able to find the cutoff frequency. So these graph indicates that all the high frequency components are boosted in pre-emphasis, and in de-emphasis it is indicating that we are recovering the signal back here. All the high frequencies are attenuated and all low frequencies are regained its amplitude levels. So from the experiment conducted, we can write the result. We observed the cutoff frequencies for pre-emphasis after plotting the frequency response is 1.6 kilohertz and de-emphasis 1.9 kilohertz. How to verify this? So we consider the value of R and C for our design like this. We assumed for our design C is equal to 0.1, T is equal to 75 micro second. So here if I substitute R and C values in the cutoff frequency expression, Fc is equal to 1 by 2 pi Rc, I am going to get 2.122 kilohertz. That is the standard values if I use. Because we have used the resistance value near 820 ohm. Therefore, we are going to get here cutoff frequency on substituting the values of R and C 1.9409 kilohertz, which is approximately matching with our results obtained. Thank you.